Okay, so let's go ahead and jump into the question and get started. All right, let me go ahead and bring up my display. Adding a new source here. Let's see, it's over. There we go. Okay. So this is the question that we will be working through for today. And first, let's just go through, read the question, and make sure that we know what we're being asked to do here. So this question tells us that the average number of weeks that an individual is unemployed is 17.5 weeks, and that we know the standard deviation of that is 4 weeks. We then want to know that in a sample of 50 individuals, what is the probability that a random sample of 50 people has a mean that is within 1 week of the population mean? So there's kind of a lot that's going on here. So let's try to break this down and see exactly what we're doing. So we have the population, and the population has a mean of 17.5 and a standard deviation of 4. From this population, we're going to pull a sample, and the sample is going to have an N of 50. So we're going to pull 50 people from that entire population for our sample. We then want to, in this case we'll actually say X bar because it's a sample. We want to know the probability that that X bar, that average of the sample, is going to be between 1 of the population. So the population was 17.5, so we want plus or minus 1. So what is that specifically? Well, that's 16.5 to 18.5. So from now, maybe we can start to see a little bit of a roadmap of what's going to happen here. What we're going to find out using a z-score eventually is the probability between those two values. So if we kind of zoom in here and try to picture what a z distribution looks like. We've got our x-axis, and in the center we have the mean. So in a standard normal distribution, that would be 0 with a standard deviation of 1. But just to have it be more general, we'll have it be our mean. And then on either side, we'll start going up and down by 1 standard deviation. So this will be our mean plus 1 standard deviation, and our mean minus 1 standard deviation, and so on and so forth. So that would be mean plus 2 standard deviations, or mean minus 2, and continuing on. And that gives us what we call the normal bell curve. Typically drawn a lot better than that. So then what we know from here is that any given, let's choose a point here, any given point on that curve has a corresponding z, which is kind of like your x point where you are along that number line. And you also have, way too large there, this area underneath the curve to the left, and that is your p-value. It's defined as the probability that a given score will be less than that z-value. You could also have the corollary, so if you look at this entire area, that's defined as 1 minus your p-value, and that's defined as the probability of getting a result that's higher than your calculated z. Okay, so let's back up a little bit there and see what's going to happen in this problem. So in this question, we don't quite know what our z-scores are yet, but if we just kind of erase these points and just imagine that we use just generic z-values, we have our mean here, and we're going to go a little bit above it, 1 week greater, and a little bit below it, and that's going to give us 2 z-values. The one on the left is technically going to be negative because we've gone a number of standard deviations below the mean. And what that's going to allow us to do, and those z's, by the way, are going to be the same because both of these differences are just 1. What that's going to allow us to do is calculate this area, which is what we want. So this is the probability for our mean plus or minus 1. So from here, this is our roadmap. We're going to solve for these z-values. We're going to consult a t-table to find the probability, and we're going to remember that the t-table probability is from negative infinity to that z-value. So we're going to get 2 p-values. And then we're going to see that the probability that we want is the probability of the positive z minus the probability of the negative z. That's going to give us this area in the middle. Okay, perfect. Now we can kind of zoom out of that region and go back to our question. So we have the 2 values that we're looking at, and all we need to do at this point is figure out the z-scores for each of these. So what's the formula for that? When we're going from population to sample, z is equivalent to x bar, or the x of interest, minus the population mean, divided by the population standard deviation, divided by the square root of n, how many you have in your sample. So let's do this first for 16.5. That'll be 16.5 minus 17.5 divided by 4 over the square root of 50. So just plugging in all of the values that we have. And this gives us a value of negative 1.76. So let's zoom right back into our probability graph here. This z, instead of writing z, now we can write negative that's way too large, 1.76. So this tells us that 16.5 is 1.76 standard deviations below the mean of 17.5. So that's what a z-score is. It's how many standard deviations you are away from the mean. And when we have a normal distribution, that's directly correlated to probabilities. Okay, let's go right back out and do our second value. So let's do 18.5. We'll have 18.5 minus 17.5 over 4 square root of 50. And let's see here, calculating this out. Interestingly, or maybe not so interestingly if you're on top of your stats, we'll actually get the same value, but positive. So that's 1.76 instead. Let's really briefly touch on why this happened, why we got the same value. And it's because we're going the same distance away from the mean, just on the opposite direction. So this difference up here that we're calculating, it's the same difference, just with a different sign. Okay, zoom back into our figure. And we can now replace this z with positive 1.76. And we're almost done solving this problem. Now we have our 2 z-scores. We need to figure out the probability values for each of them, and then figure out the probability in between them. So to do this, we will consult our z-table. This is a z-table. It's a little bit overwhelming, to be quite honest. There's a lot going on here. But essentially what this is showing us is getting your z-score. And the z-score itself is broken up into its first decimal place in the column and your second decimal place in the row. So once you've found the row and column place where your number lies, you'll be able to find that value. So first, let's go ahead and find 1.76. Now, notice all the values here are positive. I'll touch on that once we found our number. So we're looking for 1.76. So I'm going to go to the side here and start, my face is covering it, 1.7. And then, let's see if I can fit this in here. Just barely. Okay. 1.7 is this row, and the 0.6 is in this column. So let's make that a bit larger. We'll come across and we'll come down. There we go. 0.9608. So what does this tell us? Going back up to the figure here. So this tells us, grab that number one more time, 0.9608. So this tells us that the probability from negative infinity all the way to positive 1.76, the probability of your population value existing in that entire range is 0.9608, or there's a 96% chance that the sample mean is going to be in that entire range, all the way from negative infinity all the way to, this was related to 18.5. Okay, we have that. We need one more value. We need the p-value for negative. This is something interesting here. If we look at the graph, it's symmetric. Not the way I've drawn it, but it's supposed to be very symmetric. So ideally, when it's drawn properly, you'll see that everything is mirror. You can mirror everything along the central axis. So if you kind of imagine with me and we mirror this all over, if we go from positive infinity down to this negative value, that probability will also be 0.9608, and the probability under the entire curve is 1, because 1 is equivalent to 100% probability. There's a 100% chance your value will be somewhere on this curve. So now if we want to get negative infinity up to that value, we'll do that 1 minus that value, minus the 0.96. So that gives us a probability of being from negative infinity to our negative 1.76 of 0.0392. Okay, so as long as the absolute value of your z-score is the same, your probabilities will both add up to 1. We're so close to being done, you guys. So now, what we figured out our z-values. We figured out their related p-values. Now we just need to get the area in between them. So that's going to be 0.9608, probability going all the way to 1.76, minus the probability of going and stopping at negative 1.76. Okay, so that's 0.9608 minus 0.0392, which gives us our final answer, finally, of 0.9216, or if we want to write this as a percent, 92%. So going way back out to the whole question here, and I'm going to do some rearranging so we can see everything. We've ultimately determined that if we take a sample of 50 people from the entire population, the probability of the mean of that sample lying between 16.5 and 18.5 is 92%. So using this, we were able to do some statistical analysis, do some z-scores, do some probability under the curve to figure out what percent of our sample is expected to be in a particular range. So I hope this helped you guys, helped you understand this concept a little bit better. I hope to see you guys on some of my next streams. Bye for now.